We are absolutely drowning in data. I mean, think about it. A self-driving car trying to navigate a busy street, or even just your phone trying to get a perfect lock on your location. All these systems need to track things. But what happens when the information they get is messy, incomplete, or just plain noisy? Well, that's where this brilliant little tool called a particle filter comes into play. Right, let's frame the problem. Imagine you're trying to track a submarine in some really murky water. You can't actually see the sub. All you get are these little pings from its sonar every now and then. Each one of those pings is a clue, sure, but it's never the whole picture. So the question becomes, how do you figure out where something is when all you have are these partial, noisy clues? This is exactly the kind of problem particle filters were born to solve. And this gets right to the heart of it. See those Ys down at the bottom? Those are the observations. That's the stuff we can actually measure. The sonar pings, the glitchy GPS signal. But what we really care about is the signal up top, the X's. That's the submarine's true path. The whole game, the entire point of this, is to use those messy observations to figure out the most likely path of that hidden signal. Now, to really appreciate why particle filters are such a game changer, you have to understand the world they operate in. It's not neat and tidy. It's a world filled with chaotic, complex, and sometimes totally contradictory data. It's the kind of messy reality that, frankly, most older methods just couldn't cope with. For a long time, the gold standard for this kind of thing were tools like the Kalman filter. And they're great, but they have this one huge weakness. They assume the world works in a straight line. That it's linear and predictable, like a ball flying through a vacuum. Particle filters, they don't make that assumption. They are built from the ground up for the messy, nonlinear chaos of the real world. They give us these incredible approximations, right where those older, more rigid models would just completely fall apart. So how in the world do they handle all that chaos? Well, it's pretty clever. Instead of trying to find one single perfect answer, a particle filter just unleashes this massive swarm of detectives on the problem, all at the same time. And each one of those little detectives is what we call a particle. Now, it's not a physical thing. A particle is just a single, complete idea, a hypothesis. So if we're tracking a car, one particle might guess, okay, the car is right here going 50 miles per hour. But another particle might say, nope, I think it's actually over there, and it's going a little bit faster. They're all just competing guesses about what's really going on. And this is the real key. A particle filter doesn't just use like 5 or 10 of these guesses. It uses thousands, sometimes millions of them. This swarm of particles creates this incredibly rich statistical picture of what's happening. It's like a living cloud of possibilities. Yeah, some guesses will be close, and a lot of them are going to be way off, but together, they map out the whole landscape of what could possibly be true. Okay, so you have this huge swarm of guesses. How does it stay smart? How does it avoid just being a random cloud of noise? It all comes down to a really simple but incredibly powerful 3-step loop that just runs over and over and over again. This is the engine of the whole thing. First, the entire swarm of particles predicts where the target might go next. Then a new piece of real-world evidence comes in, and the algorithm updates how believable every single one of those guesses is. And finally, it resamples the entire population, basically betting big on the good guesses and getting rid of the bad ones. This cycle just repeats, constantly sharpening the final estimate. Let's break that down. The first step is prediction. Some people call it the mutation step, which is a pretty cool name for it. Every single particle moves forward in time based on some model of how the world works, like the laws of physics for a moving car. But here's the important part. A tiny bit of randomness gets added to each particle's movement. This lets the swarm spread out and explore new possibilities, which keeps it from getting stuck on just one bad idea. Next up is the update step, and this is where reality hits. A new measurement comes in, that fresh GPS coordinate or that sonar ping. The algorithm then looks at every single particle's guess and compares it to this new piece of evidence. How close was it? Based on that, each particle gets a likelihood weight. Guesses that were pretty close to reality get a really high weight. Guesses that were way out in left field get a weight of basically 0. And now for the part that honestly feels like magic, resampling. This is where the algorithm builds a brand new swarm of particles for the next loop. But it doesn't just create them randomly. It samples from the old population, but with a critical twist. Particles that had higher weights are way more likely to be chosen and even duplicated. And those particles with terrible weights, they're almost certain to be wiped out. It's like the swarm is reborn, but it comes back stronger and way more focused than before. That resampling step is so fundamental, it's worth taking a closer look. Because it's not just some clever programming trick. It's basically digital natural selection, playing out thousands of times a second inside a computer. It is literally survival of the fittest for ideas. And don't just take my word for it. One of the source papers puts it perfectly. It says, the process is a genetic type algorithm where particles undergo mutation and selection, constantly refining the estimate. See, the prediction step with that randomness, that's the mutation. And the update and resample steps, that's selection, where the environment, the cold, hard data, gets to decide which ideas survive and reproduce. And here you can see the power of that in action. Look at the left side. You've got the particles after an update. They're still kind of spread out, right? But then, on the right, after resampling, look at that. The bad guesses, those lonely outliers, gone. The good guesses have been cloned, creating this dense new cluster right around the most promising area. The filter is focusing all of its brainpower where it matters most. And the speed of this is just staggering. This whole loop, predict, update, resample, can happen over 1 million times a second on a modern computer. This is what allows the filter to track things in real time, constantly refining its cloud of belief with every single new bit of information it gets. So we've seen how this incredible process works. Let's talk about the impact it's had. Because this isn't just some obscure thing for academics. It's way more than a clever algorithm. It's a fundamental tool that helps us make sense of a really messy world. Now, a quick heads up, if you go diving into the research papers, you're probably going to see a more formal name, sequential Monte Carlo, or SMC methods. But the name actually tells you exactly what it does. It's sequential because it processes data one piece at a time as it comes in. And Monte Carlo, well, that's the classic name for any algorithm that uses repeated random sampling to get a result. And even though this feels like a super cutting-edge machine learning technique, its roots go back surprisingly far. The basic ideas of using computational mutation and selection were being explored way back in the 1950s by giants like Alan Turing. But it wasn't really until the 1990s that these ideas got hammered into the powerful tools we have today, with these key papers finally giving us terms like bootstrap filter and, of course, particle filters. So where does this all matter in the real world? Well, the list is huge and it's incredibly diverse. In robotics, it helps a machine figure out exactly where it is in a room. In finance, it's used to model the wild, unpredictable swings of the market. In weather forecasting, it helps generate more accurate predictions from noisy satellite data. And yep, even in the GPS in your phone, it's working to clean up the signal and give you a rock-solid location. Basically, anywhere you find a dynamic system and messy data, a particle filter is probably hiding in the background, doing its job. When you step back and think about it, this ability to computationally pull a clear, true signal out of a noisy, confusing world is one of the most powerful tools we have ever built. And as this tech gets faster and even more sophisticated, it really makes you wonder, if we can teach a machine to find the truth hidden in all that noise, what are the limits? What can't we eventually track and understand?